Find the sort of syntax first for the useful tools that you may need. Where the pendant of performance for efficiency and speed. Caution's crystal clears the sky with triple equals and try catch, avoiding stuff that sucks and parsing better numbers out of stretch. At last the golden shining mail of modularity. When namespace closure imports long defend integrity. For polished skills in JavaScript, the treasure trove this is. Now raise your sword and strike your shield with these best practices.
In this level, we'll be looking at speed, how to improve it and how to measure it. Many new developers think that the only way to improve performance is through complex algorithms that manage data more efficiently on the server side, or through a generalized improvement to the bandwidth of a user's internet connection. But there are subtle and often overlooked methods in the JavaScript language that you can begin to incorporate immediately, and that on a broader level will have a noticeable impact to the speed of your web applications. Additionally, often it's very important, especially in this day and age, to test multiple implementations that produce the same result in order to make the best decision about which implementation provides the best user and developer experience. To that end, we'll examine ways to illustrate that speed and time data so that you can make the best choice about which implementation is best for the task at hand. And with that, I hope you enjoy and hold carefully to the pendant of performance. Welcome back. This is level 2 of JavaScript best practices. I'm Jason Millhouse, and this section is about loop optimization. Let's take a look at a common for loop scenario where memory access may not necessarily be ideal. The first thing we'll have here on the right is a treasure chest object. Inside that object, we'll have 10,000 gold coins. We'll have the crown of speed as a magical item. We'll have an array of necklaces. And we'll also have a function called openLid. Now, if we wanted to log out all of the necklaces found in our treasure chest, we would have a little log here that says you've found the following necklaces. Following that, we could do a loop. Now, we've set up our loop parameters in a normal fashion where we loop over the entire length of the necklaces array and log out each one of the necklaces in that array in turn. That would produce, you've found the following necklaces: ruby, pearl, sapphire, and diamond. Now, this is not the best way to execute loop control, because at the start of each potential loop cycle, the program is going to need to find and retrieve several things. First, it will need to find the value of I. Then it will need to locate the treasure chest object, within which it will need to find the necklace's property. After finding the property, it will need to reference the array pointed to by the property, and then finally the length, because that's what we need. So out of all those steps, which ones can we actually eliminate safely? Because any intermediary step to finding what we want is just lengthier processor death time, right? So we want to make sure that we can get rid of as much steps as we can. All we're interested in during the loop control is that single length value and the loop counter. So we don't really need all of these other little steps that we take to find that length value. If we use cached values to curtail all of the lengthy repetitive access, you'll find that your applications improve in speed. What we'll do is we'll scoot our stuff down here, and we will assign the length of the necklaces array to this new variable called x. This will use all of the accesses that we had before, all of those steps, but it's only going to happen once. Now, inside of our loop, we'll use that x variable as the controlling parameter. As a result, the majority of all those extraneous steps have now been eliminated. Every time you help your processor out with some savings, that's going to mean more speed. And so let's check out and see what we've actually saved in our moderately simple example. So now, during loop control, memory access only needs to retrieve the value of I and then retrieve the value of x. Then we do need to add in our one-time cost in creating our new x variable. What does that mean? That means, well, we created the variable x in memory, that's a step. And then there are also the 4 steps that we saw before in actually retrieving the length value from the array inside the object. Now, if you can tolerate a little math here, we've got 2 steps for every loop. That means that we're going to do 4 executed loops and then a single check to stop. So that's 5 total starts of the loop parameter. So 2 times 5 is 10 steps for the processor just in memory access. Then we'll add in those 5 extra steps in the creation of that extra x variable. So a total of 15 steps of strictly memory access to execute just one loop. Seems pretty good. Let's check out the difference. In our previous version, we took 25 steps to figure that out. So the difference, of course, is 10 steps of savings. Now that may not seem like a lot, but let's check out what happens when we grow our data considerably. What if we had 10,000 necklaces? With large data amounts, this improvement is really going to improve results. You can see that when we have 5 steps times 10,000 executed loops plus 1 check stop, we get 50,000 memory access steps. Oh my God. But when we have 2 steps times 10,000 executed loops and 1 check stop, we only have 20,000. Then we add in our paltry 5 extra steps to create that x variable. See how that doesn't matter very much? And we get 20,007 memory access steps. Now, what's the difference there? 30,000 steps of savings. You can see how you are assisting the processor quite a bit by caching values. So we've saved all of those steps, really cool, but we can be even better organized if we place that control variable that we've created inside the parameters of the loop. Let's take a look. First, we'll scoot our treasure chest down here and we'll give ourselves a little bit more space inside of our loop parameters, and surprise, a comma is going to allow us to execute multiple statements within that very first parameter of our loop. Now what we can do is scoot our variable over and bring it down into the first parameter of the loop. A cool thing here is that we can now get rid of this var that's on the outside of the x. It's now unnecessary because that comma is going to tell the compiler that more variables are about to be declared and maybe even assigned. By creating both of these variables in the loop parameter, we now have signaled that they're actually only intended for use inside this loop. We've also limited the processor burden of declaring multiple variables with that var keyword. Now, something to take note of here is that JavaScript doesn't have any natural garbage collection. That's right, if we were to, check this out, log out the x variable after our loop, we get a 4. And that's because JavaScript does not scope to blocks. So any of the variables that you declare inside your loops, they're going to be available after the loop. Weird. And they may actually overwrite pre-existing globals, so you have to name your variables very carefully. Now, you may have noticed that a good approach to take when dealing with this kind of repetitive data access at depth is to store in a local variable any property or object or array item that is used more than once inside of a function. So the moral of this story is try to avoid that repetitive access at depth. And in our current code, we can even find a new place to further streamline this process. Let's take a look. See that console log in there with treasurechest.necklaces? That's another access of a property within an object, and we're going to do that every single time, looks like, in the loop, right? So we want to try to avoid that repetitive access. Let's see what we can do. So we'll make a new variable and we'll call it list, and it's going to be the array of necklaces. And we'll just assume that this list variable is going to get used someplace later in our code that we don't see yet. But by creating that list variable, we now can use it inside of our log without accessing the treasure chest object. Now you can see if we drop that list variable down and scoot it over, we will be logging out the ith index of the list variable. And we've avoided that extra step of accessing the treasure chest each time. On a broader level, there are other ways to optimize the loops that are inside your code, and one way is to make sure that you're choosing the best kind of loop for arrays. If you want to just deal with each index inside the array, your best bet is to stick with for loops instead of for in loops. Now, to see why the regular for loop is often better for performance, let's go ahead and add a few methods to the array prototype. Here we go. Here we have a new method on the array prototype called countType, and you don't really care what it does or what the code is inside this function. You just need to know that it would now be available to all arrays inside of our program, including that necklace array over inside the treasure chest. We'll scoot that down, and we'll also add another prototype method called remove all. You don't care what it does, but you can check it out later if you'd like. Just know that it's another array method that we have added to the array prototype. So now that we have added a couple methods to our array prototype, let's see what happens when we change this existing loop structure that lists all the necklaces to one that uses instead a for-in approach. You will see in a moment why this kind of sucks and it's going to impact the performance of your code. So we get rid of all of our loop parameters here, and in their place we put for p in list. That means for every property inside the list, and that is going to come in very key in a second. If we were to now run this code and we would see the results of our console log, we would see you found the following necklaces: ruby, pearl, sapphire, diamond, remove all, count type. Well, I don't want the remove all necklace, and I also don't want to wear a count type necklace. But the reason this is happening is because using a property approach to access indices is going to result in adding in all the methods that have been added to the array prototype. So if there's ever any additional methods on the array prototype, those are going to be included inside of your properties. Very strange if you only were concerned about the indices of your array, right? The reason that is because methods that you're going to add to the prototype, not the existing methods, but the ones that you add to the prototype, are going to become enumerable just like the indices in the array. Now, the moral of this story is that you really should only use a property approach when you really want to get to every single property of that array. Otherwise, stick with a for loop and you will have exactly the functionality that you desire. We're going to give you a few challenges on loop optimization, and we'll see you back in the next section.